Right, everyone, let's get started. Right. As usual, we're going to start off with a quick recap of what we covered last week. So, samples and populations. We've discussed those definitions. Now, terminology. We know that the measure of location, the average that uses all of the data, is the mean. And if you work out the mean of a sample, then the symbol that you would use would be X bar. Okay? Now, what about the mean of a population? A Greek letter? Okay, so looks like that. Okay, mu or me. Okay, so the mean is a measure of location. It tells us about the size of the values. Okay? A measure of dispersion is a statistic that tells us about spread in a data set that uses all the data, would be the standard deviation. Okay, but there's also the variance. Okay? There is a relationship, of course, between the standard deviation and the variance. What is that relationship? The standard deviation would be the square root of the variance. Okay, so if you work out a sample standard deviation, the symbol that you would use would be S. Whereas if you work out the standard deviation of a population, we would use the symbol sigma. Okay, another Greek letter. And of course, because we know the relationship between the standard deviation and the variance, if you work out the variance of a sample, then the symbol that you would use would be S squared. Whereas if you work out the variance of a population, you would use the symbol sigma squared. Okay, so the first topic that we covered last week was confidence intervals. Okay? Now I gave you this scenario. I said, imagine that we're interested in the average house price in Newcastle, and we randomly select two houses. Okay, one is worth £100,000, the other £400,000. So we all agreed that the sample mean, X bar, would be £250,000. But I asked you the question, would that be a precise estimate? Okay? Would that be a precise estimate of the true mean? And you all said no. Okay, what were the reasons for that? Okay, very small sample size. Okay, just two houses. Another reason? One house is 100k, the other house is 400k. A lot of spread, yeah? Large dispersion. Okay? For those two reasons, that wouldn't be a precise estimate. Whereas, second scenario, we all go to some other city in the UK, we randomly select 100 houses, they're all worth more or less 250k. X bar would still be 250k, but now it would be a more precise estimate of the true mean. Okay, so what is the motivation behind confidence intervals? What's the need for them? In our research, what do we usually look at? Samples or entire populations? Samples, okay? So we study samples, but why do we study samples? Because ultimately we're interested in the wider populations, okay? So you calculate sample statistics, okay? Sample statistics, we always use English letters from the Roman alphabet. Okay, we calculate these, but we would like to know how precise they are as estimates of the true values. Now, the next new topic that we're going to look at is called ANOVA. Okay? But I can promise you that this new topic, ANOVA, you will find it very, very simple as long as you're comfortable with hypothesis tests. Okay? So last week, what did we cover? In the lecture, I think we only spent about 10 minutes, 15 minutes talking about t-tests. Okay? And the reason I introduced the topic was because, of course, they're featured in the computer practical. Okay? But t-tests, hypothesis testing, is a very complex subject. Okay? So you did very well, actually, to complete the computer practical last week. Okay? Because there's that relationship between t-tests, okay, hypothesis testing and ANOVA, we're going to go back to t-tests. Okay? We're going to think about the ones that you covered. What did you cover last week? What kinds of t-test? There was the... Okay, there's the one sample t-test, there's the two sample t-test, and there's the paired t-test. Okay? Right, so before we look at the t-tests, you do have the equation, of course. Okay, you have the equation for a confidence interval. Okay, you've got it on page 20 of your notes. But it isn't important, okay? It isn't important for you to remember equations, okay? The important thing is being able to interpret the output. Okay? The way this component of the module is assessed is a project. Okay? I'm going to give you the project next week. I might show you a question from it later on in this lecture, just so that you're not worried about it. But you see, you've only got 4 weeks to do it. Okay? That's why I want to give you it in lecture 5, so that we've covered most of the material. Okay, so there's no reason, there's no need for you to be remembering these horrible equations. But it doesn't hurt for us to look at the equations sometimes because, well, what would we want to know about confidence intervals? What affects precision? Okay, well, if you look at the equation, you can work out what affects precision, how wide they are. Okay, n. What do we know n stands for? Lowercase n stands for sample size, okay? That will affect precision. What about S? That's the standard deviation. That will affect precision. What about T? You can see T in the equation. What does T refer to? T refers to the level of confidence that you're working to. Okay? What is the common level of confidence? The standard level of confidence, the default in Minitab. The default level of confidence is 95%. Okay? If you're 95% confident, there's only a 5% chance you're wrong. Okay? So it's a good thing to work to a high level of confidence. Okay, so in Minitab, I'm just going to construct a confidence interval. And I want you to interpret the output. Okay, so I'm just going to make this a bit larger. Okay, so what was the command for a confidence interval? It was stat basic stats 1 sample t. And I'm just going to use some summarised data. Okay, let's imagine that we've got a sample size of 16, a sample mean of 500 grams, we'll use that example from last week, the box weights, a standard deviation of 2, and you'll see in options default 95% confidence. Okay, so I would like you to interpret the numbers in brackets. Boxes of cereal, we're looking at the weights, so what's the data type? Is it quantitative or qualitative? It's quantitative. Is it continuous or discrete? It's continuous. So we've taken a sample of 16 boxes. The sample mean is 500 grams to 3 decimal places. Okay, that's why it says 500.000. The standard deviation is 2 grams. Now, how do we interpret the two numbers in brackets? That's the confidence interval. How do we finish off this sentence? We're 95% confident that the true mean, the population mean, is between those two numbers. You all okay with that? Okay, that's the interpretation. Now, what I would like you to do is make a prediction. I'm going to change one thing. Okay? I'm going to change the standard deviation from 2 grams to 8 grams. Okay, I won't click OK yet because I want you to make a prediction. Will the interval get wider or narrower? Do you all think wider? Okay. We'll see if you're right. Were you right? Okay, so it obviously makes sense to everyone that the standard deviation is a measure of dispersion. The larger it is, the more spread out the data is. Okay, the wider the confidence interval will be. Okay, I'm going to change something else now. So I'm going to go back to stat basic stats 1 sample t. Standard deviation going back to 2 grams. Sample size, instead of the sample size of 16, the sample size will be 64. I want you to make a prediction. Okay, hands up who thinks the interval will get wider. That's less precise. Hands up who thinks it'll get narrower, more precise. Okay, well done if you thought it would get more precise. Can you all see that? Okay, we're comparing this confidence interval to this one. So again, it obviously makes sense to you because you predicted correctly. As sample size increases, we're learning more and more about the population, so therefore our estimate of the true mean will be more precise. So I'm going to change one final thing. Okay, what's the final thing that will affect precision? Okay, so we've changed standard deviation, we've changed sample size. What's the third thing that will affect precision? The level of confidence. Okay, so that was a 95% confidence interval. What if we're working to 99% confidence? Okay, that's better, isn't it? 95%, there's a 5% chance you're wrong. 99%, there's a 1% chance you're wrong. What will happen to the confidence interval? Who thinks it will get wider, less precise? Some of you. Who think it will get narrower, more precise? Some of you. Okay, so a bit of a disagreement this time. Okay, what's happened? You need to compare the first one to the last one. What happened? It got wider, it got less precise. Now that's the most difficult one to predict correctly, because would you all agree that narrow, precise confidence intervals are better than wide, imprecise confidence intervals? Would you all agree with that? So, 95% confidence. 99% confidence sounds better, doesn't it? However, there has to be a drawback. There has to be a disadvantage to increasing confidence. Because if there wasn't a disadvantage, what did we say last week? You would always work to 100% confidence. Okay? The disadvantage is, as you increase confidence, the intervals get less precise. Okay? Because you have to be correct. What was the analogy we used last week? You support a sports team, you support a football team in a league of 20 teams. At the start of the season, you say, I'm 90% confident my team will finish between 5th and 15th. But you could say with 100% confidence your team will finish between 1st and 20th. Okay? So as confidence increases, the intervals just get wider. So you have to stop at some point. What point do you stop at? What's the typical level of confidence that we work to? What was the default in the Minitab? 95%. Okay, so that's confidence intervals, but what about the one sample t-test? In your notes on page 23, you're given the steps. Okay, you're given the steps that you would work through when you're carrying out a hypothesis test. Okay, so with the t-tests, there is this assumption. Okay, look at bullet point 1. What's the assumption? The data is normally distributed. Step 2, you set up your hypotheses. Okay, you will have a null hypothesis. What's the shorthand notation for that? H0. And you have an alternative hypothesis, shorthand notation HA. Okay, you'll collect some data, you'll analyse it, and Minitab will give you a p-value. Okay, how do we interpret that p-value? Well, you've got a table, haven't you? You've got a table at the top of page 23. Okay, any t-test, okay, any hypothesis test, okay, they all give you the same thing. They all give you a p-value. Okay, that is how you interpret p-values. So, you've got an example in the notes of the one sample t-test, okay, and it relates back to the rocket engine thrusts that we talked about in lecture 1. But I want us to try to do it for these box weights in column 1. Okay, so I won't use the summarised data anymore. I want you to imagine that, this is our data. So, if you were writing down the null hypothesis for a one sample T, H0 colon the true mean equals, what does it equal? If it's a one sample t-test, it just equals a number, okay, some value. So, I want you to imagine that for the box weights, okay, you work at this supermarket, okay, I know it's not a marine engineering example, but remember, all of these tools and techniques are transferable, okay? That variable is continuous, okay? Weights of ships, that's continuous. So, I want you to imagine that you work at the supermarket, you've always believed that the true mean is 499 grams. Okay, what would the alternative hypothesis be? HA colon mu doesn't equal 499 grams. Right, so I'm just going to use the same command as before. Stat basic stats, one sample T. I'm not using summarised data, I'm going to use that raw data in column 1. And to start off with, I'm not even going to tick that box. Okay, I'm not going to tick that box that says perform hypothesis test. Okay, I'm just going to change the confidence back to 95 and click OK twice. Okay, so imagine we are testing this hypothesis. You've always believed the true mean was 499 grams. Okay, let's interpret that confidence interval together. We are 95% confident that the true mean is between those two numbers. So, look at this again. If someone asked you this question, is it feasible that the true mean could be 499 grams, what would you say? No, because 499 grams doesn't lie inside the confidence interval. So can you all see that the question can be answered just by looking at confidence intervals? You don't have to actually do the hypothesis test, okay? But this time, I am going to, okay? So back to one sample T. This time I will tick perform hypothesis test and type in 499 and click OK. Can you see that the confidence interval is exactly the same as before? Nothing's changed. But now, what have we got? We've got a p-value. Now, a p-value will never be exactly 0. However, Minitab only gives you these answers to 3 decimal places, okay? So this is 0.000, okay, 0 to 3 decimal places. So how do we interpret that answer? If your p-value is that low, what's your interpretation? If your p-value is that low, you would say that is overwhelming evidence against the null hypothesis. You all happy with that? Now, one sample T tests, they're quite difficult to understand, okay? They're quite abstract, okay? Someone said last week in the computer practical, well, you know, why would someone said in the computer practical last week, why wouldn't your null be mu equals 500.013? Can you all see that's the sample mean? So someone asked the question last week, why is this the null? Why isn't that the null? It's because you set up your null and your alternative before you collect your data. Okay? So this is just a theory. Okay? You've got a null and you've got an alternative. You then test it by collecting data. Okay? You collect data. We've now got these answers and we know we can reject the null. So that's the one sample T. The next one in the notes was the next one in the notes was the 2 sample T. Okay, remember that we're discussing this in more detail now because the next topic, ANOVA, it's so simple as long as you're comfortable with this. So, a 2 sample T test. You've got 2 groups, okay, 2 samples. Sample 1, sample 2. So, again, you've got certain assumptions. Okay, what's the assumptions of the 2 sample T? Well, again, normality, but what else? The other assumption would be that the dispersions, okay, the dispersions are equal in both groups. As usual, you set up your null and you set up your alternative. Okay, so the null here H0, and the true means are equal. Okay, that's your null. So what does the word null actually mean to you, generally? I know English might be a second language to many of you. The word null, N-U-L-L, does it mean anything? Well, null in English kind of means zero, nothing, no difference. So would you all agree that this is like a logical starting point? Okay, if you've got two groups and you want to compare them, the null for a two-sample T would be the true means are equal. Alternative, they're not equal. So, this example was a comparison of the rocket engine thrusts, okay, because now there was two different engines. So, you produce histograms to assess the normality of the data. And if Minitab gave you this output, what would you say? Which rocket engine gives you the largest thrusts? It's clearly rocket 2, yeah? Just by looking at the descriptive stats. But you can never look at just descriptive stats, okay, to draw a conclusion like there is a significant difference between these groups. That word significance has a special meaning in statistics, okay? You can only say that you have a significant result, okay? You can only say that groups are significantly different once you've looked at the p-value. So, that's your p-value, 0.012. Is that a significant result? .012. Okay, we'll look at our table again. Okay, NS. Okay, the bold NS in this table, what does it mean? Not significant. Okay, so when you get big p-values, okay, p-value over 0.1, you would say, well, that's definitely not significant. Okay, our p-value for the rocket engines was 0.012. Okay, so what would we say? What's the conclusion? Strong evidence against the null. Okay, so the null is that the means are the same, but we're rejecting that. Okay, there's strong evidence against that. So what was the example that we very briefly looked at last week? Okay, columns A and B. What was this? 10 boys, 10 girls, take an exam in maths. And what did we say? If you are only interested in these 20 children, okay, if these are the only 20 children you're interested in, what could we do? We could just work out the means, couldn't we, of each column? And that's all you'd have to do. Okay? But if you're interested in making a comparison between boys and girls generally and their abilities in maths, then you need the correct statistical test. So, how would we write the null for that example, columns A and B? Okay, you've got males, you've got females. So how do you write the null? H0 colon mu m equals mu f. Does that make sense? Just males and females. And what's your alternative? The true mean for the males does not equal the true mean for the females. Okay, I'm just going to very quickly run that test. Okay, this will be the final example that we look at. And I want you to interpret the output. Okay, so two sample T. And the best graphical display Okay, the best graphical display, I would say, when you're comparing independent groups, would be box plots. Okay, so who's doing the best at maths? The girls, yeah? But is that difference statistically significant? Look at the p-value, 0.401. What would you say? It's big. It's way over 0.1, so this is a non-significant result, yeah? We don't have the evidence to reject the null. We would retain it instead. Does that make sense? Right, so that's the 2 sample T. And what did we say this data was? You've got 10 boys who take an exam in maths. And the same 10 boys take an exam in maths the year after. Okay, what test would you do? Okay, what test would you do to know whether the boys had got better or worse? What would you do? Would you do a 2 sample T? Or would you do a paired T? You should do a paired T. Okay, so I'll just analyse this data. Didn't get a chance last week. Okay, how many box plots did you see when it was a 2 sample T? 2. So how many box plots will we see now? Okay, you only see 1 box plot. Okay, so when you do a paired t-test, why do you only see 1 box plot? Okay, you only see 1 box plot when it's a paired t-test because the test is actually done, okay, the test is actually carried out on the pairwise differences. Okay, now I've just worked out the pairwise differences. Okay, what do you notice about them all? The pairwise differences, can you see they're all negative? So what does that mean? If the pairwise differences are all negative, it means that all of the boys did better in year 2. Okay? Because the null for a paired T would be that there's been no change. Okay? What would our conclusion be looking at our results? P-value 0 to 3 decimal places. What do you do when p-values are that low? Do you reject the null or return it? You reject it, don't you? So would you all agree here? We need to reject the null. But what does that mean? Why are we rejecting the null? Did the boys get significantly better or did they get significantly worse? Okay, look at the descriptive stats. Okay, look at these numbers. What's the answer? We reject the null because the boys got significantly better. Okay, you see they could have got significantly worse and that could have ended up with a significant result as well. Right, so that's the t-tests. Now what's ANOVA and how does it relate to t-tests? Well, there's one word that's important that we define, and that word would be factor. Okay, a factor. Now, I'll ask you this question and see if anyone can give me the right answer. Would you all agree that that data in columns D and E is the same as that data in columns A and B? It's just stored in a different way. Can you all see that? I think it's easier to answer my next question by looking at the data in this format, columns D and E. The question is, When you do a two-sample t-test, how many factors have you got? Two? We haven't actually defined what a factor is yet, so don't worry that you don't know, but the answer is 1. Okay, there's one factor. What is a factor? Well, with these tests, we have independent variables and we have dependent variables. Okay, so you might want to make a note of that. We have independent variables and we have dependent variables. What's a factor? A factor is an independent variable. So, look at columns D and E. Okay, one of these columns contains the independent variable, the factor. Which one is it? The independent variable would be gender. Think about the question we're trying to answer. Okay, what is the question we're trying to answer here? Is maths score dependent on gender? Would you all agree that that's the question we're trying to answer? Is maths score dependent on gender? So therefore, maths score is the dependent variable and gender is the independent variable. So the question was, how many factors have we got? What's the answer? 1. How many levels does it have? 2. Male, female. So would you all agree, when you do a two-sample t-test, there is one factor, and how many levels does it have? 2. Right, so, what about if you were comparing carpets in terms of durability? I want you to imagine that you've only got 2 carpets. I know you see 4 carpets there, but I've highlighted 2. What if you had 2 carpets and you were comparing them in terms of durability? What test would you carry out? If there's only 2 carpets, what would you do? The two-sample t-test. But what if you've got 4 carpets? What if you've got 4 carpets? Well, how many factors have you got here? 1. How many levels does it have? 4. This test is called one-way ANOVA. Why is it called one-way ANOVA? How many factors have you got? 1. So when you have one factor, okay, when you have one factor at any number of levels, you can carry out this test called one-way ANOVA. So what can we now say about a two-sample t-test? A two-sample t-test is simply a special case of one-way ANOVA. Okay? Because one-way ANOVA is one factor at any number of levels. What's a two-sample t-test? One factor at 2 levels. Okay? So it's got its own name, the two-sample t-test. Okay, so one factor, any number of levels, one-way ANOVA. Finally, I want you to imagine that you've got a biologist. Okay, a biologist studying levels of zooplankton in different lakes when different supplements are added. Okay, so there's different lakes, there's different supplements, and the biologist is going to measure zooplankton. So how many factors has the biologist got? 2. Factors being lake, how many levels? 2. Supplement, how many levels? 3. 2 factors. Why is it called two-way ANOVA? Because there's 2 factors. So it's that simple. In your notes, you've got this information about ANOVA. But ANOVA is simply an extension of the two-sample t-test. Okay? I used the word factor. I said that when you've got a two-sample t-test, that's one factor at two levels. Okay, the reason I was telling you that is so that you can understand what two-way ANOVA is. Two factors. But you could say that with a two-sample t-test, there's two groups. Okay, you null for a two-sample t-test, mu1 equals mu2. Okay, what about if you've got k groups? What's your null? All the means are the same. Same assumptions as a two-sample t-test. Okay, normality, and also equal variance. So in the notes you've got an example of a one-way ANOVA, and you've got an example of a two-way ANOVA. So we'll just look at this one. This is the lengths of eggs, and we've got three different birds. We've got the robin, the hedge sparrow, and the reed warbler. Okay, so, what if we only had the robin and the hedge sparrow? If we only had two groups, it would just be the two-sample t-test, but we've got three groups. So we compare them using one-way ANOVA. This page just mentions the assumptions, the fact that we're interested in normality, but some of you asked last week about, my histogram doesn't look particularly symmetrical or bell-shaped. Okay, when your sample size is small, you shouldn't really expect your histogram to look perfectly symmetrical, perfectly bell-shaped. Okay, here are some histograms for the lengths of the eggs. Sample sizes are small. The histograms, they don't look perfectly normal. So as well as histograms, you can also construct probability plots. Okay, so you'll get a chance to do this in the computer practical. So what are we looking for with a histogram? How do you know whether a data set is perfectly normal? What would your histogram look like? Symmetrical and bell-shaped. With probability plots, if your data is perfectly normal, the red dots will fall on the line perfectly. Okay, and you can see that this isn't happening. Okay, these data sets are not perfectly normal. However, we do have confidence intervals. Okay, can you see the curved lines? Okay, they're confidence intervals. The points fall inside the confidence intervals. Okay, this is indicating that these data sets follow the normal distribution quite well. Okay, so you're checking these assumptions just like you would for a two-sample t-test. Now, what if this was your output? Okay, can you all see that even though it's slightly more complex, there's more groups, can you see that you've still got the p-value? What's the p-value? 0.005? Okay, so what's the decision? What's the conclusion? Do we retain the null or do we reject it? You reject, yeah? This is a significant result. The p-value 0.005. But can you all see that there's something else that we need to do now? If you got a significant result for a two-sample t-test, what would you know? If you've got a low p-value for a two-sample t-test, what would you know? The two groups are different, yeah? Because there's only two groups. But how many groups do we now have? 3. So can you see that you need to do something else? Because this p-value is telling you what? A low p-value indicates that you should, what should you do? Reject the null. What's the null? The means are all the same. We're rejecting that we're saying the means are different. But, which ones are different? Okay, are they all different? Or is it just a couple of them? So, you always follow up an ANOVA by doing multiple comparisons. Okay, so in your notes, you've got this information on page 31, multiple comparisons. Okay, multiple comparisons on page 31. Something called two keys test. Okay, so this is just an option. This is just an option in Minitab. Okay, you will select in the computer practical two keys test. Okay, so how is it useful? What it gives you is confidence intervals for the differences between the groups. Okay, look at this section. Robin subtracted from hedge sparrow. Okay, Robin subtracted from hedge sparrow. What do you see? Lower. Okay, lower. Can you see that's a negative number? Upper, a positive number. So can you see that crosses 0? Okay, that indicates that there's no significant difference there. What about Robin subtracted from reed warbler? Lower is a positive value, and that's also a positive value. So can you see that that confidence interval doesn't cross 0? So that means there is a significant difference between Robin and reed warbler. And finally, the other comparison, hedge sparrow subtracted from reed warbler. Is there a significant difference here? Negative number, positive number. So what would we say? If the confidence interval goes from a negative number to a positive number, it means 0 has been crossed, so therefore no significant difference. Okay, so what was the only significant difference? The only significant difference was Robin and reed warbler. Okay, so finally in that section you've got an example of a two-way ANOVA. I'd just like you to read through that top paragraph. Right everyone, so we're looking at yields of carrots, and I want you to imagine that we've only got these 10 different treatments, A through to J. Okay, so if you're looking at yields of carrots and you've just got these 10 different treatments, A through to J, what would you do? What would you do if we didn't have the fields? If you only had the 10 treatments, A through to J, can you all see that you would just do a one-way ANOVA? Because that would be one factor at 10 levels. But because of the different fields, okay, well that's a second factor. So that's why this is two-way ANOVA. The null and the alternatives, okay, this time you've got, you've actually got two nulls and you've got two alternatives. What's your first null? What's this one here? This one here, we're just comparing the treatments. Okay? Mu A equals mu B through to mu J. And when we compare the fields, okay, that's the second factor, remember? Mu1 equals mu2 equals mu3 equals mu4. And how do we always draw our conclusions? From these hypothesis tests, what do we simply look for? p-values. Okay. Look at the p-value for the carrot yield. Okay, that's the treatment. What is it? 0 to 3 decimal places. So what's the conclusion? Is there a significant difference between the treatments? Yes, there is, because that's very low. What about the 4 different fields? Okay, 4 different fields. Okay, known as 4 different blocks. What's the p-value? 0.193. So what's the conclusion? Is there a significant difference between the 4 different fields? No. Okay, so it's as simple as that. Okay, ANOVA, you know, whether it be one-way ANOVA, that's one factor, two-way ANOVA, that's 2 factors. It's simply a continuation of the t-tests. Okay, so something that I'll just very briefly show you before we finish would be the project. Okay, so I will give you the project next week. Okay, so you will have 4 weeks to do it. Okay, that's the regulations of the of your school. So I don't want to give you it too early because we won't have covered enough material. Okay, but by next week we will have done. So there's 3 sections, okay, to the project. Section A, just a very easy quiz worth 10 marks. Section B is the main body of the project. It's worth 70 marks, and it's very similar to the computer practicals. Section C is worth 20 marks, and it's your appraisal, your critique of some research that features stats. Okay, but you know, if you look at Section A, the quiz, you're going to have your notes, remember? Okay, it's a project, it's not an exam. Section A, quantitative variables can be continuous or discrete. Explain the difference between them and give an example of each of them. Okay, so it's not difficult stuff. Okay, but it's only by next week that we will have covered sufficient material. Okay, so I'll discuss the project in more detail next week. So that's it for today, and now we've got the computer practical upstairs. Alright.
A work handout, a work hand back today.
See you later.
Yeah, thanks.
Okay.